Helena said there was a 20-second delay.
Yeah, yeah.
Right.
I think we can wait for another minute and then we can start right away.
How can we see how many people have tuned in?
16 are waiting now from the YouTube.
Oh.
Yeah, I think it's now live on YouTube, so we can start. So, good afternoon, everyone who is joining us in this event. I am Samuel Gabra, and I'm part of the Energy, Reactions and Carriers group at the Department of Chemical Engineering and Biotechnology. I'm joining you today with my other co-hosts, which are members of my group, which are Zach Bond, Kenny Kong, and Joe Gibbs. I'm very happy to be with you today, as all of us. So today we are very excited to join you all in our quest to discuss how to solve one of the world's most critical problems, which is climate change. So firstly, you might wonder, oh, I hear this word a lot. Everywhere, actually. Climate change, climate change, climate change, and more climate change. So what's actually happening? So today we want to discuss with you, what does it mean by climate change? Do we have any solutions for climate change at the moment? Can we implement these solutions? And if we solve this problem, would we be able to save ourselves, our planet, and our lovely Antarctic wild animals? So I'll start firstly with giving you an introductory slide about what's climate change. It can give you a bit of sense of what's happening. And we can then start with our demos that we have. So let me first share my screen with you. So can you all see my screen now? Okay.
This is the world. That's you and that's me. The world has the perfect temperature to keep all living things alive and happy. This temperature depends on a balance. The sun's heat goes to Earth to make it warm. The sun's heat bounces back to space to make the Earth cool. When this balance is lost, the climate changes. The Earth's climate has changed many times before. This is called natural climate change. It's caused by volcanic eruptions, changes in the sun's energy, and changes in the Earth's orbit. Greenhouse gases also make the Earth warmer. They trap heat from the sun. Greenhouse gases are like a blanket covering the Earth. It started in the 1700s. Humans started to build more things. We burned coal to make electricity. We burn oil to make our cars and planes move. We use chemicals to make things. We cut down lots of trees. We burn gas to cook food. We dump lots of trash on landfills. We plant a lot more rice. All these things release greenhouse gases. Remember the blanket over the Earth? Because of humans, it got much, much thicker. When I get hot, I sweat. I even get dizzy. Imagine the Earth. Because it's hotter, glaciers and ice sheets are melting. Seas are rising, storms are getting stronger, some places are getting dry, even the sea is getting warmer. All living things are in big trouble.
So I think that gives a little bit of an introduction about the greenhouse gas effect and how this causes climate change. So let me stop here and firstly ask the people who are watching us through our YouTube channel to like our video to know whether you are still corresponding with us. And if you are having any questions during this session, we are very happy to take your questions through the comments section. So So yeah, it seems that some people are claiming, and there is a big claim that the Earth is warming, there is climate change. So is this actually happening? Do we actually have a climate change problem? Do we have the greenhouse gases and carbon dioxide emissions affecting us as human beings and affecting our planet? This is a question that we always had in our minds as researchers, and we wanted to see whether we can actually get this effect in the lab. So we prepared a short experiment in order to demonstrate the effect of greenhouse gases and see whether we can have any observations in the lab. So may I ask Elena that we play the video for our first experiment?
Eleanor's asking what to play. Which file, Sam?
I think I can just play the first video from my laptop.
Sounds like a good idea.
Yeah.
Yep.
So can you see my screen now? Wonderful. We will start by describing the experimental setup that we have, in which here we have two separate systems that's composed of two electric heaters that heat two volumetric flasks that are placed at the same distance from the heater as a control of the experiment. For the flask on the left-hand side, it's mainly filled with air, while the flask on the right-hand side is filled with carbon dioxide that we will be feeding from this conical flask by inducing a reaction between simple vinegar and bicarbonate of soda. This carbon dioxide will be fed into the flask that we will have the temperature recorded using a thermocouple inside the flask, and this thermocouple is connected to a data logger for the two flasks. And as you can see now, the temperature for both flasks is almost the same at room temperature, which is expected. Now we will describe how we can generate carbon dioxide and what would be its effect. We would have in this conical flask a reaction between vinegar and bicarbonate of soda that we simply brought from Sainsbury's. We will add a small amount of the vinegar to the conical flask first, and then afterwards we will add 1 spoon of the bicarbonate of soda to make the chemical reaction that would produce carbon dioxide that we need to conduct the experiment. After we add the bicarbonate of soda, you would notice that we would have a strong effervescence from the conical flask, which indicates the chemical reaction that is taking place. After we add the bicarbonate of soda, we would try to seal the system as quickly as possible to prevent any of the produced carbon dioxide from escaping, to maximize the concentration of carbon dioxide in the volumetric flask. Now, since we are feeding carbon dioxide, we will start heating of the two electric heaters, where we will see that as the temperature rises in both flasks, we would have different temperature due to the presence of carbon dioxide and air. As you can see in this graph, as we increase the temperature of both flasks, we would observe a higher increase in the flask full of carbon dioxide, and this is expected because carbon dioxide will store and hold the radiation coming from the heater, keeping the temperature higher inside the flask, which is of a very similar effect for what we encounter in our real world due to greenhouse gases like carbon dioxide, leading to an increase in temperature of our Earth. Okay, so it seems that we have the effect of carbon dioxide is already clear. We know that it's happening, and the carbon dioxide and the other greenhouse gases has a significant effect, even at the effect of small containers, small vessels. So let me just start by asking our panelists here if what do they think about this, and if they have any other opinions about what's happening. So let me start with Kenny to ask him, apart from the rising sea levels, from the temperatures that are rising due to the effect of greenhouse gases, what other negative impacts of the carbon dioxide? So maybe if it's just an increase in the sea level, that's fine, we can afford this, it's totally okay. If it's a bit of warmer temperature, we can go to the beach and enjoy a nice tan there. But what about the other effects that we have? Can we even live a worse life than we are living now because of this effect?
First, thanks for the question. First, I would say that increase in the sea level is not just fine, it's quite serious because it can cause of damage. Like for example, it can destroy the plantations, it can cause floods, and also the weather, as you notice now, it becomes more extreme. There's more frequent extreme weather like hurricanes and also drought. And also, some kids in the future might not be able to see snow anymore. They're so sad if you think about it. But there's not just the effect of the global climate change. It also the increase in the global temperature can also favors the growth of the blue-green algae, which can cause the aquatic life to be destroyed by the eutrophications. This is the effect of the carbon dioxide on the temperature. The carbon dioxide, as we know, is slightly acidic, and when it dissolves in the ocean, it can cause the ocean acidifications, which is also another way to destroy the aquatic life. And this is bad news for the fish.
Oh,
besides this, yeah.
That seems pretty serious.
Yeah, it is. It is very serious. Like apart from this carbon dioxide, if you just think that it just affects the environment, it's actually not true, because carbon dioxide was found to able to impact the human directly. For example, their research found that carbon dioxide can cause people to experience anxiety and stress. And also, their research showed that on when they put 700 parts per million carbon dioxide on mouse, the mouse will have experienced some respiratory muscle failure, and also some hormonal abnormalities. So it's a serious problem.
Wow. So if it's that serious and it has effects on human beings and animals and also fish, so I'd like to ask, so now we know there is a problem. We know that we are a bit causing this problem by our activities. So I just want to ask Joe, how do we produce this carbon dioxide? What are the main sources for this carbon dioxide? Because if we know the sources of this carbon dioxide, maybe we can help reduce our emissions and have a happier life. So, Joe, what do you think?
Sure, thank you for the question. The majority of carbon dioxide emissions come from the burning of hydrocarbon fuels. And regarding what are the main sources of carbon dioxide emissions, your largest sources are transportation, and this is through the burning of fossil fuels for our cars, trains, trucks, planes, and ships. Then also another large source comes from the generation of electricity, and this is through the burning of predominantly coal and natural gas. And then finally in industry, industry is another large producer of carbon dioxide. And this is mainly from the burning of fossil fuels to provide energy to these industrial processes.
Wow. So it seems that most of our activities that we do in our daily lives, which is going out of bed, breathing, causing carbon dioxide to emit, taking a car, going to work, emitting carbon dioxide, taking a plane to visit back home is emitting carbon dioxide. So it seems there is almost no way to solve this problem. Almost all of our activities that we need every day emits carbon dioxide. Cars, planes, our power plant. So Joe, are you saying that we should stop producing any electricity? We should have no electricity in our homes. We shouldn't study. We shouldn't do anything with energy. Maybe our audience can give us some insights about this. Maybe our audience can ask if there is any technical jargon that we are using that they might not understand, and we are very happy to respond to these questions. But let me now go to Zach and ask him, so Joe proposed that everything that we do in our daily lives is causing a problem. How we solve this carbon dioxide emissions problem, or is it inevitable? Can we already do anything about it?
So though there are many different greenhouse gases, we're focusing our talk largely on CO2. CO2 has been recognized as perhaps the most sort of the largest contributor to mankind's own contributions, I should say, to the greenhouse effect. So if the problem is that there is too much CO2, now the concentration of CO2 is going up in the atmosphere, we have two approaches that we could use to help to reduce the CO2 concentration. The first of these is quite simple, really. We just stop producing it. Now, obviously, we can't stop producing it through our own respiration. That would be quite a big ask. But we try and stop producing excess amounts of CO2, and particularly that CO2 that's originating from the carbon that we dig up from underground. That's the carbon that was buried underground millions of years ago. And it's this carbon source which is damaging, because we're burning it all and sending it up into the atmosphere as CO2. So that sounds like an easy thing to do, but sadly, as you point out, most of our things that we enjoy doing, eating nice food, having buildings to live in, and electricity for sort of all of our activities can be serious polluters in terms of greenhouse gas emissions. So the other approach is to take a more active approach to removing CO2, rather than just stopping emitting it and letting the CO2 levels fall slowly. CO2 stays in the atmosphere for a very long time, naturally. We could try and remove it from the atmosphere. And there's an awful lot of research at the moment on different ways of removing CO2, either by filtering it out of the air, which is a very difficult thing to do because it's present in quite low concentrations, or by planting lots of wood, lots of trees to take in carbon dioxide as they grow, and then making sure that that carbon stays locked away from the atmosphere.
Okay, okay. So what you are saying, Zach, is that if we want to capture carbon dioxide, it's either we enjoy doing things that we enjoy doing, or stop enjoying them and live a pretty boring, miserable life without cars, without planes, without trucks. So this is what you are saying.
I should say that it's not just about enjoying life. There are lots of very necessary parts of our world that we've built around us to sustain the population. For example, we need to produce fertilizers on a vast scale, and even just feeding this many people that we've got on the planet with the fertilizers we produce is another heavy emitter of CO2. So it's not just about enjoying ourselves.
Okay. So if it's not about enjoyment, it's about essentials. I found a very nice solution for this, which is one day I found a leaflet saying that sun is the solution. So we will replace everything that we have with solar panels, very clean, no emissions. I haven't smelled any of carbon dioxide out of a solar panel before. So solar panels is the solution. Depend on the sun, have solar panels everywhere, and that would be an easy solution, no?
So yes, so we could replace all of our energy sources with renewable energy sources. Might in their level produce a lot less CO2 than burning fossil fuels would, or even in some cases no CO2. That would be brilliant, and that is largely where we're hoping to go as a species. Now we can do that. You know, we've produced solar panels and wind turbines, but it's not just about energy production. As I mentioned, we've got fertilizers, steel, and producing concrete. Even things like producing meat. These are all very, very heavy emitters of greenhouse gases. And not only that, but they're very difficult processes to improve in such a way that they produce fewer greenhouse gases. And they'd be very expensive to improve as well. So sort of a bit of a problem here between the amount that we can do to decarbonize energy industries and things like that, and the amount that we need to reduce our CO2 emissions by. There's a big gap. So all of these industries that I mentioned, they're very difficult to improve in that way. So that's a problem, really.
Okay. So it seems that we would inevitably emit some carbon dioxide from some of these applications.
Yeah, and that's where this idea of removing CO2 from the atmosphere to counteract those industries that are very difficult to decarbonize comes in and is really important.
Okay, so taking from this, so what you are saying that emitting carbon dioxide is inevitable, I would firstly like to welcome all of our audience who come from places across the world. We have people joining us from Spain, Malaysia, Albania, and India as well. So with this, I wanted to ask Kenny, since you are from Malaysia and we have people here from Malaysia, why don't we have all of our efforts to remove the carbon dioxide in one country, since every country is emitting their own emissions, and this will not affect other countries. So I'm emitting carbon dioxide in India, this will ruin the life in India, and that's it. Or I'm emitting it in Egypt or in the UK, and that's it. So can you tell us why we are affected by this across the world, or is every country mainly affected by their own emissions on a small microclimate?
Yeah, so as you imagine, the air is not static. So the carbon dioxide will just not, when you release from, for example, from Malaysia, the carbon dioxide, I'm from Malaysia as well. So the carbon dioxide will not just stay at the atmosphere of carbon dioxide above Malaysia. It will just circulated around the earth. And as we have discussed earlier, the carbon dioxide causes the global climate change. So it's the issue that happening across the world. So we have to deal with it as a part of the world. So it's not just, of course, like if every country reducing their carbon footprint, that'll be good. But the whole global everyone should take part in reducing the carbon dioxide.
Okay, so now, as a summary for our first discussion, we firstly know that we will still be having this problem of carbon dioxide emissions. It's already affecting us, and we can observe it in the lab. So, luckily for us, throughout the research in the last few decades, we found that there are some magical substances and some materials that can capture the CO2 that we are emitting, and it can release it in a different place. That's quite interesting. So we wanted as well to make sure that this is something that we can observe in the lab, something that we can see, something that we can present to anyone, saying that we are trying our best to save our environment. So I'd like to share with you our second experiment, which is about capturing this carbon dioxide, which is, as Zach mentioned, one of many greenhouse gases that contributes to the climate change. We firstly start with the experimental setup that we have. We have, firstly, the flame burner or the fuel burner that's present here, where we have the window that shows the flame, and also a place where we put the fuel and the filament that goes through the flame, where we start with the glass wall that removes tar, a place for the catalyst or the particles that we have, the sampling bomb that would draw the sample, the carbon dioxide sensor that would detect the carbon dioxide in the stream, and a Raspberry Pi that would log the data from the carbon dioxide sensor. We then start by setting our fuel burner. This is what is the fuel burner is composed of, where we have a wick inside that would burn the fuel and would release it upwards. And the bottom compartment, we have the fuel, the liquid fuel that we have, and a wick that connects the fuel with the flame. I'll show you now how we can set this up, where we can fill in this compartment some of the liquid fuel, which is in this case isopropanol, one of the many hydrocarbons that are present, or we can get from the nature. We then put in the wick inside. and afterwards we want to get this wick through the device. So we have a special tool that we can grab the wick with. And as you can see, we set the tool first and then we grab the wick with it until we get it. So in the two experiments we will do, we firstly will pass the flame through the whole system without having the particles that would capture the carbon dioxide and measure the carbon dioxide concentration. And in the other arrangement, we will put the particles, and in both cases, we will measure the carbon dioxide concentration and compare it. In the first setup, we do not have any particles. So we will just have the flame passing through the carbon dioxide sensor to see what level of carbon dioxide we get without the capturing particles. After we have the system in place, we will just light up the wick with a torch. And we can see the flame inside now, where it would release carbon dioxide and other combustion products upstream and would be sensed by the carbon dioxide sensor. We get the data from the Raspberry Pi data logger. We wait a bit of time and then we extinguish the flame. As we can see in this graph, once we have the combustion in the system, we have a huge release of carbon dioxide. This concentration of carbon dioxide, which is shown in red, is very high and cannot be released to the environment in such concentration, or otherwise we would have the heating and thermal effect of the carbon dioxide, as we have already shown in the earlier experiment. So what we can do regarding this is we will be using particles in order to take away some of this carbon dioxide. So how we are capturing this carbon dioxide? In our system, as you can see, we have the carbon dioxide passing through the whole system, but we will fill in this bed or compartment with special particles or special material that can capture the released carbon dioxide from combustion. In our case, this material is calcium oxide. We can get this material from nature, and with only simple preparation, we can just have this material. Once we have the bed full of this material, once we will pass the carbon dioxide, a significant proportion of this released carbon dioxide from the combustion would be captured by such particles. In the case of these particles, you should be handling them with care because they are a bit dusty. And that's why I'm wearing a mask at the moment. We then seal the system back, and then we put it in place. And then we repeat the same experiment as before, where we will have a combustion of the fuel through the wick, passing all of the products across the system, which now has the particles, and see whether this would lead to any change in the concentration of carbon dioxide in the output. Now we will again light up the system with a torch. And we will wait a few seconds. As you can see, the particles are starting to fluidize due to the gases moving through the system. We will wait a bit of time for the system to be in a steady state. And afterwards, we extinguish the flame as we did before. As you can see in this graph with the blue line where we have now the particles of calcium oxide, we can see that the concentration of carbon dioxide in the outlet stream after the particles decreased significantly compared to the concentration without the calcium oxide, which means that these particles are effective in capturing carbon dioxide from the combustion product stream, where calcium oxide was converted into calcium carbonate. But what to do with this calcium carbonate? This is what I'm about to show you now. Now we have these particles after the reaction of calcium oxide with carbon dioxide to produce calcium carbonate. We can get them out from the bed, in which in order to be able to reuse these, we have to retrieve them from the system, put them into a container, and then place them in a place with high temperature to have the release of carbon dioxide that we can then store separately, and the calcium oxide that's produced we can reuse again for capturing carbon dioxide. This is how the material would look like. We would just put it in a furnace to be regenerated and to be used again for many, many times. I would like to send special thanks to everyone who contributed to these experiments: Kenny, Zach, Alex, and Eva. Thank you.
Okay, so it seems that we have an experiment. The experiment worked, and we can see that we can have some magical material that can capture our carbon dioxide. So we received a very good question from Zhongki Hu. I apologize if I'm saying the name in a wrong way, about how realistic and cost-effective is carbon capture technology. And this is a really good question. But before answering this question, I would like to remind our audience that to watch us through the live stream, to like our video, to show us that they are interacting with us, that they are watching us, and to ask whichever question that can come to their mind, whichever they think it's silly. Science starts by very silly questions. So you don't know whether your question can inspire people around the world about this specific topic. So please don't be shy to ask any question. So coming back to Zhongyi's question, I want to divide the question into two parts, which is how realistic and how cost-effective is the carbon capture and technology. And I would like to invite Zach to answer such a question. given his expertise about the carbon capture and storage systems. So Zach, do you have any insights about Zungi's question, which is, as you can see, is a very good question?
Very good question, yes. How realistic is this? Well, there are already several examples of power plants which have been retrofitted with carbon capture apparatus, and an awful lot has been learnt. There have been a lot of mistakes made by the people implementing the plant. I say mistakes, things that you couldn't really foresee on paper. But when you come to do a trial in real life, you learn all of the difficulties which are faced. So one of the big problems is that if you want to remove the CO2 from the exhaust gases, the material that you use you want it to not react with anything else in those exhaust gases from a combustion process, for example. And that's really tricky because there are a lot of substances in exhaust gases. So there's a lot of chances for odd reactions to happen that you weren't expecting. So there's a lot of people working on this. And so we're getting quite close to a number of the different means of carbon capture. We've demonstrated just one here of being quite cool, really. The cost question is something which I think we need to first discuss a little bit more about before we find out why aren't we doing this already. Clearly there is a reason that it's not being done on a wide scale, and that has got to do with the cost, but I think we need to discuss a little further before we answer that one.
Okay, that's I think that's a very nice answer to both parts of the question. And I think we have a more technical question from our audience, from Jorge Apunto Gomez, who is asking if calcium oxide was a catalyzer. And it seems quite a technical question, which I would invite Kenny for this question. And to tell us what's calcium oxide, whether it's a catalyzer, to answer Jorge's question, and to tell us if there are any other material that can be used instead of the calcium oxide, or is it the only material that we can use? So you can tell us more about the material in general.
Yeah, so the calcium oxide is used for the carbonations of the they have the carbonations reactions to form calcium carbonate. So whether it's a catalyst or not, is still there are still people believe that it's a catalyst, but a lot of research actually just show that it's just materials that can react to form calcium carbonate. So this is still open to some debates, but I personally believe that it's not a catalyst, and there are quite a lot of literature to back me up, but also you can always find literature in both sides. But back to the questions, is there other materials that can be used to capture this carbon dioxide? Yeah, of course there is. For example, amines. Amine solution can be used to capture carbon dioxide because, as Zach have mentioned just now, it also have a properties to capture the carbon dioxide and not to have reaction with other chemicals in the exhaust gas. But if you want to use this amine solution, we need to produce this amine solution, and the process of producing this amine solution will produce carbon dioxide. So what we do not want to do eventually is to produce something, to use additional energy to produce something which causes more carbon dioxide to produce in the same time, which eventually make our process to be carbon positive. No, we do not want that. And the good thing about calcium oxide is there's a lot of calcium oxide in Earth. We can easily get it from, for example, from the seashell. So it can be quite cheap. Like back to the questions that some audience asked earlier, how cost effective it is. Just on calcium oxide, it can be quite cheap because you can easily get it, and also it is non-poisonous. That means that it is quite environmental friendly. So yeah, calcium oxide is a better solution, I would say, in this application.
Okay, that seems nice. So now we know from Zach that the process is feasible and with some logistics can be cost effective. And we know from Kenny that there are this calcium oxide, what's the material, and if there are any other material that can cause this to happen. So maybe I might be wondering now, so everyone can get their own calcium oxide at home. They can have their calcium oxide at the end of their catalytic converters in the car. We can have calcium oxide everywhere to remove all of the carbon dioxide on Earth. So I want to ask you, Joe, do you think this is a good idea to have calcium oxide everywhere and to stop emitting carbon dioxide from anything? Would you use calcium oxide in your car, for example?
That's a good question. I mean, ideally, yes, you'd just remove carbon dioxide everywhere from everything. But there's several reasons, I think, why it's not. Firstly, there's sort of applications where it might be difficult to use and regenerate calcium oxide for CO2 capture, something like the car, for example, which is why sort of we need alternative, cleaner sources of energies to run in parallel with it. There are other key challenges that go along with the capture of carbon dioxide with calcium oxide, and that is that the material degrades over the cycles of capture and regeneration, reducing its capacity to remove CO2. And this is mainly attributed to the sintering of the absorbing particles. And because of this, the calcium oxide material must be replaced continually over the process with fresh material. And then finally, and perhaps the principal reason why carbon capture is not implemented in all applications is because it currently lacks economic incentive. Because capturing carbon dioxide requires extra energy, as we've mentioned, it means more fuel must be burnt, it means additional operating costs, it means there's initial capital to set up a process like this. So simply, it's more expensive than the alternative of not capturing CO2 at all. And I guess an analogy is like throwing lit on the ground. In the short term, it's much easier and cheaper to just throw lit on the floor and not take it home and recycle it. So unless there are incentives to change our behavior and do the right thing, changing towards carbon capture is slow.
Okay, that seems like a nice answer to this question. So it means that this is not only a technical problem, it's also an economic problem and societal problem, that we need to tackle all of them in a multidisciplinary fashion. And with this, I also wondered that we now have the calcium oxide producing calcium carbonate. And in the video, we showed that we can regenerate this calcium carbonate by heating it up to release carbon dioxide. But this doesn't make any sense, because we are capturing the carbon dioxide and we are releasing it again. So do you mind, Zach, explaining to us why does this make sense that we are capturing the carbon dioxide and release it again, and whether this is of any use to our quest for solving the climate change problem?
So Joe mentioned regeneration of the material that we use to capture the CO2. And so actually what we've shown we've shown the step where the sorbent material, in our case calcium oxide, has captured the CO2 either from fuel, from exhaust gases from a power plant, or we could even envisage a material that could capture CO2 straight out of the air, for example. But then what we need to do is to process that material to get pure CO2 out of it. And that's this regeneration step. And in the case of calcium oxide, that's done, or calcium carbonate as it becomes, that's done by heating it up to a very, very high temperature. And then it will react to form calcium oxide and gaseous CO2 again. Now, in order for this whole scheme to work, we need to take that pure gaseous CO2 and we need to make sure that it doesn't escape into the atmosphere. And that's where the chemical engineers run out of their sort of sphere of influence, and it gets handed over to the geologists of the world, who are pretty certain that we can pump CO2 into geological features underground, and that it will be very stable there and held there for a very, very long time. In some circumstances, it may even react with the rock underground to form a solid, and that would be really good. Solids are much easier to store than gases. So if we, so that's the whole scheme for carbon capture and storage, but we need a material that we can use to extract CO2 and move it into a different reaction environment to extract that CO2 as a pure substance. That's the ultimate goal if we need to stick it underground. And this process of having a material that we're moving between two different reaction environments is where we get a term called chemical looping from. And if you want to research a little bit about this at home, you can use that term chemical looping to find some interesting papers or articles online to read. And it's this process of regenerating the sorbent which takes more energy to do, to drive off the CO2 as a pure stream. So if we want to do chemical looping or carbon capture, we're going to need to use more energy. We might need to burn more fuel to capture that CO2. And that's where this extra cost comes in. We don't get it for free.
Okay, so it seems that, okay, we are now having the calcium oxide, having the calcium carbonate after carbonation with carbon dioxide, releasing this carbon dioxide underground. And with this, we have some technical challenges, some economic challenges, some societal challenges. And with this, I would like to take Zonggi's question again, which is, while working with entrepreneurs and billionaires who are concerned about the environment, lift off the economic burden of this carbon capture. So again, I think Zonggi is revolving around the question, which is the economic challenge that we have. So we believe that any kind of incentives in terms of economic merits or some tariffs or carbon tax or any kind of economic model would be very helpful in this. Any kind of economic push from the governments or the entrepreneurs or billionaires would help in this quest. And I think with our, if I would like to summarize our event today or our talk today, we went through firstly to tell you what's climate change, what are the greenhouse gases production that lead to this climate change. We know now through very simple experiment in the lab that we can replicate the effect of greenhouse gases on climate change on a very small scale. We discussed this and we went through capturing this carbon dioxide that's being released, storing it. We discussed what are the benefits and what are the advantages of this. But to leave you with a very small take-home message is that climate change is a problem. We all should contribute to it, whether we are young or big. We all have our roles of it. If we work in the field, then you can be working as a geologist, as an engineer, as an economist, or any other subject that can help in this specific field. So if you are young and watching us now, 12, 13, 14, 15, and you are wondering about your career, many careers can contribute to this specific quest to save our planet. But even if you are not in a field that you think can help, even your small actions towards the sustainability of our planet, the emissions of climate change, of greenhouse gases, and the climate change would be very helpful. And we encourage everyone to go through this process by trying to use resources that do not emit many greenhouse gases, to use renewable energy, and to push as a society for a more greener and less carbon dioxide emissions from us as a society. With this, I would like to thank our panelists here, Kenny, Zach, Joe. I'd like to thank Elena for organizing all of this. I would like to thank Eva, which helped in arrange this behind the scenes. We also very much thank our audience who are joining us today. We are very happy to answer any of your questions behind the scenes in an email, or if you text us, we will try to answer your questions as soon as possible. Thank you all, and I hope for you to enjoy a happy weekend, happy Easter holidays weekend. Thank you, Zach. Thank you, Kenny.
Sam, have we got time for some question answering? We've got a few outstanding questions to deal with.
Okay, yeah. So we have a question from an anonymous attendee saying that want extracting the carbon dioxide from calcium carbonate require fuels that produces carbon dioxide. I'm not sure about our time, but we can answer this very briefly. I can leave the floor to you, Zach, to answer this very briefly before.
Where we're at the moment in our energy mix, yes, yes, it does. So this is the thing, is that there's no such thing as a free dinner when you're dealing with thermodynamics. In order to capture that CO2, if we take the case where we've got a power plant and we want to reduce its CO2 emissions, and that power plant is running on a fuel that emits CO2, we would have to burn more fuel in order to run the CO2 capture plant beside it as well. Now, net, we would have a reduction in the CO2 emitted. However, we would have an increase in the amount of fuel that we needed, and therefore actually a decrease in the sort of overall efficiency of the process. If we define efficiency in terms of the electrical energy we get out of a power plant versus the fuel that's coming in. So that's why carbon capture is a costly process, and so it costs more money to carry it out, and that's people aren't going to pay more money for their electricity, or companies aren't going to pay more money to capture CO2 until they are forced to by large global sort of schemes which would tax CO2 emitted to the atmosphere. And this is another reason why relying on very few people, rich people like Elon Musk has been brought up for this. This is a problem which is far bigger than one or two people. This is a global problem involving every country in the world that needs to participate in this. Yes, rich entrepreneurs could help out with this, but one thing to note is that Elon Musk produces electric vehicles and PV cells to help with the switching us onto renewable energy, but he makes a lot of money by doing that. There's no money to be made out of capturing CO2, and so it's very difficult to get businesses or entrepreneurs involved, because it's a costly process, and until CO2 is taxed, there's a price on CO2, there's no financial incentive for rich people and rich companies to do this.
That seems like a very nice answer, and it's a nice recap that we will not have a free dinner, but
Yes.
but while we cannot have a free dinner, it's better to have a bit of a lighter dinner now than paying the price later, 20 or 30 years ago, while we have our sea levels rising without us being able to manage this. So if we have to take an action without a free dinner or with a free dinner, we have to take an action now, and we have to bear the consequences, either the economic or the technical,
before it's too late to save our environment. Thank you all for this. Thanks for the audience. Thanks for very nice questions. And we are still happy to take any of your questions that you can send us by our emails or through the department's website. It's always a pleasure to speak about science and its effect on the environment, and to feel that we are trying to engage more people in our quest to save the planet. Thank you all. Have a lovely afternoon and have a lovely weekend. Bye.